Geology of National Parks class. Welcome to a lecture on Canyonlands National Park. This place is spectacular. It's Utah's largest national park. It's a wonderland of spires, mesas, canyons, fins, arches, potholes, Indian ruins. 337 acres on the Colorado Plateau. It was established as a national park in 1964. And it contains sedimentary rocks of Paleozoic and Mesozoic age, as much of the Colorado Plateau does. The Colorado River flowed in a meandering style, meaning kind of back and forth in these big turns and loops across an ancient landscape that was at sea level. The other river that flows through this national park is the Green River. And those two meet up in kind of the southern part of the national park. And the Colorado Plateau was uplifted, and the river simultaneously, or both rivers simultaneously, began to erode downwards. And that resulted in what geologists referred to as entrenched or incised meanders. And that's what this park is famous for. These beautiful canyons, deep cut canyons with high walls, where the Green River over here and the Colorado River kind of cut through this flat-lying area with all these exposed sedimentary rocks. Now this park, if you come in, this triangular area here is kind of the area in between the Green River here. If you can see the Green River, this is what I mean by meandering. See how it loops back and forth and back and forth? That's a meandering river. Here's the Colorado, and you can see that it meanders back and forth, especially some large ones over here. And they both meet up in this area, just south of the maze. I'll talk about the maze in a second. But this area here is called Cataracts Canyon, because there's a bunch of eroded rocks that fall into the river where the Green and the Colorado kind of meet together and create intense rapids over here. But over here, you can come in. There's a road leading into here. There's a visitor center if you're on this side of the park. This is referred to as the island in the sky. It sits up there at pretty high elevations, 7,800 feet. And this triangular plateau stands high above the rest of the park, so it's a great place to get an amazing view, Grand Point view. This is Grand Point view, so this is kind of looking to the south. Okay, so that means if you were here looking in this direction, and see if you were pretending you were there now, to the right you would see the Green River, and that's this over here. So you can drive over here. This is an interesting area. It's called the Upheaval Dome. That's an area where there's a salt dome. Salt is less dense than the surrounding sedimentary rock, so it kind of migrates upwards, and as it does, it creates this dome type feature, and it bends the sedimentary rocks upwards, kind of like a cereal bowl upside down. So that's kind of interesting there. So this is definitely a great place to visit, but once you come here, you have to kind of go all the way around to the other visitor center on the southern side of the park to visit the other places like the Needles. Okay, and the maze, largely unvisited because it's very large and people can get lost there. I know it's like enter on your own caution, because there's just it's about 30 square miles of canyons kind of cutting back and forth, and you can get easily lost there. All right, so there's the park itself. It's located kind of like the southeastern portion of Utah. So right here, there's Canyonlands. And here's a satellite image showing you the meandering rivers within the canyon. And that's what we mean. So if you're on a boat, you're kind of like, okay, we're going down river and we're making this huge meandering loop to get back basically where you were before. And this occurs back and forth with these giant loops. And this typically, rivers are shaped like this when they're very close to the ocean. And the reason is rivers kind of focus their erosion kind of laterally, and they flow side to side, forming and enlarging these loops and then straightening. So it is kind of odd to find a meandering river on the Colorado Plateau because it's at an elevation, in this case like over 7,000 feet. Typically rivers at high elevations are more narrow or straighter, and they tend to cut downwards, but there's a special reason for this, for meandering river on the Colorado Plateau. Here's another view of it. Now this park has what we refer to as mesas. Okay, that's the Spanish word for table. So there are outcrops of rock that form kind of like a tabletop, rectangular tabletop. There are buttes also, which are like smaller ones. Okay. Then there are really thin spires. I think I have other images to show you that. But this is what it looks like. This is an incredible view, closer to the ground, but very steep canyons. Here's the river. Very beautiful place. A nice palette of different oxidized colors or reddish orange colors all over the place. And so what we refer to this, here's a higher up view, is an entrenched meander. Okay, so here's flat-lying rocks. That river's kind of cut its way downwards to create these entrenched meanders. That's what makes this park unique. There are also a lot of other features here. Here's a closer look with some of the rock units. The shales tend to form these gradual slopes, whereas the white rim sandstone, which you've been able to see in a number of the other images, those tend to form cliffs because sandstone's harder. Here's another view. Beautiful landscape. This is in the wintertime. You can still see snow cover on the ground. Those are people walking out to an outlook. But again, you can see mesas, canyons. There are also potholes here that the river's kind of cut through. Really beautiful, exposed, colorful Mesozoic rocks. Okay. Arches also tend to form. That's due to differential erosion. Now there might be some softer rocks below this harder sandstone unit that eroded away quicker, creating this arch feature. This is Angel's Arc. There are over around 25 arches in this park. Now, Arches National Park, which is also in Utah, has over 300. So if you really like those geologic features, Arches is the place to go. But Canyonlands has got some nice features. Here in the background, see, you can see this almost looks like the set of Westworld. Okay, there's the mesas and buttes. These are those very thin spires, very thin, exposed, typically sandstone, and they erode away along their joints, and they form these really thin, almost like building-like structures. And this area here, this picture here, is the maze. This is the area where a lot of people can get lost. Here's the kind of canyon floor, and it just winds back and forth, and you can easily get lost. In fact, during the early American history, a lot of outlaws in the region used Canyonlands National Park as a way to hide from law enforcement, because they knew where the watering holes were, because they're kind of few and far between here. It's very dry. There's only 7 to 9 inches of rain a year, so if you know where the watering holes are, that's great. So a lot of the outlaws committed crimes and then would run away into these canyons, and then the law enforcement didn't bother going into the canyons because they knew if they got lost, it could mean their lives. So they just, let it go. Okay, what you can also find here, there's also evidence of Native Americans that lived here. There's 2 different groups. One group, I think, was around in they're referred to as the Lost People, around 900 AD, the Fremont culture. Then afterwards, the Anazazis, they're around 1075 AD. And there's scattered pottery evidence that people resided in this national park. And the evidence here is this art that's alongside some of the exposed rocks here. Now what this is we refer to this as desert varnish. Desert varnish is essentially a weathering process as water kind of trickles down the canyon walls, typically like say on a sandstone or something. It'll coat the walls with this varnish that's iron oxide or manganese oxide, and it's just a weathering process, oxidation of any of the minerals that contain iron in them. And so you can scratch that off. So what they did is essentially they scratched off the desert varnish to expose the fresh rock beneath it, and they made shapes out of it. Feet looks like an alien. I don't know what that is. A wheel, okay. So yeah, so you can see some evidence of Native Americans residing in this area. It's beautiful. So a stream valley is the channel and the surrounding terrain that helps direct water into a stream. And alluvial channels are areas that have really wide valley floors, and they're typically found closer to the ocean. Bedrock channels, they typically have a V-shaped valley. So when we're thinking of a landscape, think of river valleys, right? And you can have V-shaped ones or very Y-shaped valley floors. So in arid climates like in or on the Colorado Plateau, you tend to have very narrow valleys that have near vertical walls, and that's true of the canyons in Canyonlands National Park. It's also true, this I think is from Zion. These are referred to as slot canyons, where this is incredibly steep, this huge vertical face of this canyon. And so in order to understand how rivers shape valleys, we have to understand what the base level is. And the base level is essentially the lowest point a stream can erode to. Water always kind of under the force of gravity wants to go to the lowest possible point. And so if it's far away from sea level, it's going to focus its energy downward or erode downwards to get to that ultimate or a base level. Most base levels are sea level, so we refer to that as the ultimate base level. Water has a tendency to try to make it out to the ocean. That's the lowest lying area. The ocean basins are the lowest points on Earth, so that's where the water goes. But you can also have local or temporary base levels. Okay, this can include lakes, dammed up lakes, resistant rock layers, large rivers, or in dry areas. Sometimes water will never make it out into the ocean. It just kind of go into a valley and just dry out. So the base levels essentially limit the stream's ability to downcut in the channel. So what happens is when there are changing conditions, that can cause a readjustment in what the stream does over time. Rivers are, areas where water is kind of moving through the landscape and eroding and cutting through it and shaping it. So when you have a raising of the base level, that causes deposition. And when you lower the base level, that causes erosion. So let me show you two kind of examples here. So here's a river going out to the ultimate base level into the ocean, right? When a river is very close to the ocean, its erosive power is focused on this side-to-side meandering fashion because it's very close to the base level, so downcutting isn't as important. And when you go up to higher elevations like over here, these would be referred to as the headlands of the river. The river here is narrower, and it's cutting downward to get to the level of the base level. Remember, the base level is here, so we can draw a line underneath the base level, and then the river up here is trying to cut down to get to this level. Okay, so let's pretend, us humans, we're like, yeah, let's build a dam. Okay, so what we do here, this is a dam. This is the new base. The new base level's here. So now what we've done is we've done this. This is the new base level. So what will happen to the river is that instead of being narrow and focusing on down cutting, this river will now evolve into a meandering river because it's at its new local base level. So the river here will begin to meander back and forth. So you kind of change the behavior of a river by altering the base level. And this is an artificial alteration, but natural ones can occur with plate tectonics. Like say this entire area could be uplifted higher. That could raise the base level. So here we go. If we're at the headwaters or far away from the base level, what we get is valley deepening. Okay, a really steep gradient, and the channel is very far from its base level. That leads to downcutting of the river channel. If you look at it here, this is a river channel in a valley. Look at the shape of this valley, V-shaped. Okay, that means this river here is focused on downcutting this area, and it's going to erode downwards because it's pretty far away from the base level. All right, so that creates those V-shaped valleys with steep sides. That's severe downcutting. All right, and what you typically see in V-shaped valleys are rapids, waterfalls, and that's when the stream's gradient increases significantly. That's also true of the Yellowstone River at Yellowstone National Park. Here's Yellowstone Falls, and if you notice, here's the river. This is at an elevation of about 12,000 feet, and notice the shape of the river valley, V-shaped, and that's because this river and this water is really far away from the ultimate base level, so it's downcutting. It focuses on eroding downwards, creating these steep valleys. If we take a look at Niagara Falls, Niagara Falls today is located right here, okay, but it hasn't always been here. About 12,000 years ago, Niagara Falls was actually over here, as the water from Lake Erie kind of moved through the Niagara River and then kind of into Lake Ontario. Okay, so what's happening here? Here's the Niagara escarpment. Okay, this is kind of a big change in elevation to like kind of a plateauish area up here. But what's happening is there's headward erosion. These are the head waters of the Niagara River, and the falls itself are eroding the rock at the falls slowly. So over the course of 12,000 years, the waterfalls have been migrating towards the headwaters and to their present location. So this is going to continue to happen over geologic time. Niagara Falls is going to continue moving towards Lake Erie until there are no more falls. So that's in 12,000 years it traveled, the waterfall itself traveled about 7 miles. And here's a picture of the falls. All right, different types of stream valleys, or when you have rivers closer to the base level, what happens there is you get valley widening. So once a stream approaches a graded condition or lower gradient, meaning that there's not much change in elevation, the shape of the river changes to a meandering pattern. Downcutting is less dominant and more energy is directed side to side. And what this creates over time is a floodplain with a very flat valley floor. Okay, the floodplain can be inundated with water when the stream overflows its banks, and it creates a bunch of other features. When you have a depositional floodplain, that's when you have fluctuations in the base level or changes in climatic conditions. So here's the development of a floodplain. So say we have a V-shaped valley. The river's kind of narrow, straighter, and cutting downwards. But let's pretend all of a sudden that the base level's changed, and now the river is very close to its base level. Now the river's behavior focuses on kind of moving in a meandering fashion, back and forth and back and forth. And what this does is the erosive power is focused horizontally. So there's more erosion over here and there's more erosion over here, and it starts widening this valley and flattening this valley in the interior. So over time, as the river ages and gets older and older, it develops a well-developed floodplain, kind of like what we see in the Mississippi River floodplain, all along portions of the Midwest. A very well-developed flat area here where the river is allowed to kind of meander in its own course back and forth as it evolves over time. So let's get back to kind of this unique situation, what geologists refer to as incised meanders. Incised meanders are meanders that flow through steep and narrow bedrock layers. And so what initially happens is a river forms its meandering fashion in a floodplain. And then what happens is the base level drops. And this could be due to something like the uplift of an entire area. And so what happens is if you uplift an area fast or really quickly, the meandering river, the river focuses on downcutting rather than kind of meandering and evolving that way and eroding horizontally. So it'll keep its meandering fashion but continue to downcut, and that's what's happening on the Colorado Plateau. If the river ever adjusts to its new base level, right? So if ever cuts down and gets to the base level, then it'll form a new floodplain. All right. And then the old floodplains will be flat remnants we refer to those as terraces. So you can almost think of the top of this area here was the base or the old terrace or the floodplain, the flat-lying area above where the Colorado is now, because that's where it was. When this area was at sea level, this is where the river was. But since then, this area has been uplifted and the Colorado River has cut downwards and eroded all the rocks that are found in the canyon. And it's continuing to do so because this area is still, about 7,000 feet above sea level. So that's what you see here. This is an old terrace where the floodplain used to be, and now the river's downcutting. All right, the Green River and the Colorado River. So here's the progression over time. So over time, this landscape was at sea level, and the Colorado River was, the former Colorado River, Colorado River back then, about 20 million years ago, was meandering, and this was a floodplain. But because of the uplift, it changed the base level, or the base level was lowered, and so now the river's focus is on downcutting, leaving behind these spectacular canyons. And that's what an incised meander is. And this can happen repeatedly, or if there's like a number of shifts in the base level. Here's an example of stream terraces. So here's the floodplain with a meandering river, and let's say there's a little bit of uplift, and then the river reaches its base level again. So here is the former floodplain, and it becomes a terrace, and this is the new floodplain, flattened area. Then there's more uplift, so then the river gets adjusted again, and now you have two terraces. So it almost looks like steps going upwards. And you can see this along the Wind River in Wyoming. Here are the former flat-lying areas of former terraces. So there's multiple layers here. Other depositional landforms that form from rivers, deltas. That's when a river kind of runs into a larger body of water. And typically when that happens, the velocity of the river slows down, and then the river deposits out all its sediment. Rivers carry a lot of sediment. In fact, they're almost like conveyor belts of eroded particles from different areas. And when their forward velocity decreases, it lowers the carrying capacity of the river, and you start depositing different types of beds: foreset, topset, and bottomset beds. So the size of the sediment varies in the delta. That depends on the velocity of the river. Coarse sediments are typically deposited closer to the mouth, and we refer to those as foreset beds. The finer sediments remain kind of floating in the water as the water kind of goes further out the edge of the delta, and those are bottomset beds. And so as the delta grows outwards, the stream's gradient continues to decrease. So eventually what happens is the channel, or the river channel, gets choked with sediment, and so it like dams itself, and it forces the river to divert into a new direction. So the river seeks a shorter path to the base level. And so that's what creates a number of what we refer to as distributaries from the main channel in a delta. Yep, there's a picture. So here's the evolution of a delta. A river comes out into the ocean, dumps up a lot of sediment, chokes itself, finds a new pathway to the ocean, chokes itself, new pathway, a new pathway over this, and then you get a bunch of different distributaries kind of going into the ocean and the deposition of a lot of sediment. And here are those 4 set beds depositing in the ocean. So it's really a dumping ground for a lot of sediment that's eroding from continents. So the Mississippi River Delta is the largest delta in the United States. It's a series of coalescing deltas as the Mississippi River has kind of evolved and kind of moved into different areas. Since we've occupied and built cities on the delta itself, like New Orleans, the river has become heavily channelized, and so the present delta is called the Birdfoot Delta, and it's been forming over the past 500 years. So here it is, because it looks like a crow's foot, you know, with the fingers kind of splaying outwards. So this is the current location of the delta and where most sediment is being deposited. But over the course of 5,000 years, 5,000 years ago, this is where the delta was here. Then most of the sediment was depositing here. New Orleans is kind of right on the cusp of that old delta. Then it moved over to 3, then all the way out here to 4, then to 5, and then 6 here, and there's 7. If you notice, and essentially the entire state of Louisiana is just one big river delta for the Mississippi River. So Louisiana's, a lot of these areas are just unconsolidated river sediment piled on top of each other. If you notice, delta number 1, the oldest one, is mostly covered by the ocean now. And that's because a lot of the rivers don't dump out enough sediment in this area, so the sediment settles and starts to sink below sea level. And that's why New Orleans is particularly in trouble, because they kind of channelize all the water away to the Birdfoot Delta, so this area doesn't receive as much sediment, so it's sinking. And if you don't have delivery of sediment and the sediment is settling and sinking, there are areas of New Orleans that are actually below sea level. And that's why it's so susceptible to flooding. Rivers also create cool features called natural levees, and they're raised areas adjacent to the river channel. And they form during flood events. So water, when there's a lot of discharge, typically in the spring is when you'd have flood events, but water will overtop the banks and flow out like flat sheets onto a floodplain. And it'll deposit the coarse sediment right on the banks of the river. And then after the flood event's over, that deposition leads to higher banks, and we refer to those as natural levees. Other features can form during flood events: back swamps and Yazoo tributaries. Let me just show you a picture. So here's a floodplain, okay? Here's a meandering river, and then as soon as this area is experiencing a flood, so you can see here, over here, these are the Yazoo tributaries and low-lying areas, these back swamps. But here, this is when the water overtops the river and you have a flood, okay? So the fine sediments will be deposited out here, the coarser stuff here. So as the flood waters recede and they go away, you're left behind with higher natural levees. And then as this process repeats itself, another flood stage, you have more coarse sediment depositing on top, and the natural levees are larger. So it's weird. Nature's way of preventing future flooding is more flooding. It's like a catch-22. Hey, would you like less flooding in the future? How about flooding now to prevent flooding in the future? Another depositional landform that is generated by running water across the landscape are alluvial fans. These typically form at the base of mountain fronts in really dry areas. So out west are great examples of this. When these rivers, these ephemeral rivers that don't run year round, move through really dry areas or deserts, And so when there's a major rain event, all this water collects, moves down a mountainside, and then it just kind of dumps all of its sediment at the base of a mountain front. So we find them in arid climates, mostly sand and gravel. Let me just show you some pictures. So here are some, this entire wedge of, this is deposited sediment. And this whole area is called an alluvial fan because that's its shape here. So when in these areas, when they do have rain events, it removes a lot of sandy, gravel, sediment, anything that has been mass wasting and eroding from these mountains, and dumps them out into the valley floor. This happens to be Death Valley in California. All right, then there are floods, and floods are problematic. They cause the most, they're the most destructive geologic hazard. And this happens when the stream, the water in the stream exceeds the capacity of the channel, and then the water overtops the banks, and then floods an entire area. And you can see it causes a lot of damage. You can see water most likely going into these homes and damaging the drywall, electrical. These cars are most likely damaged. That's a big problem. A lot of people live in floodplains or in areas that can receive a lot of water, or there can be just like a dramatic event like a hurricane. One comes to mind is Hurricane Harvey and the coastal plains in Texas. Those areas were hard hit. They got like something like 40 inches of rain in 3 days, so that caused severe flooding. So there's 4 different types of common floods. Although I'm not so sure about these ice jam floods. I guess it depends where you live. Anyways, there are flash floods, which are kind of dangerous. Regional floods, which what you see here, and then dam floods are kind of single events that can occur as a result of natural hazard or just human engineering error. Regional floods are just seasonal floods that result from spring rains or rapid melting of snow. This is one example in 2011 in Mississippi. People who live on the floodplain there are probably used to this. This occurs often, and you can lose your homes in this fashion. You can lose your life too, but that losing your life is more common when you have a flash flood. Flash flood occur with very little warning. A lot of times they happen in drier areas when there is actual rain because there isn't much vegetation to hold down the sediment. But the most dangerous ones are in mountainous areas. All right, so those are susceptible to flash flooding because the steep mountains kind of divert the water into channels and into low-lying areas fairly quickly, and then that can cause water levels to rise really rapidly. When we talked about the Narrows at Zion National Park, that path that you can walk through, if it ever rains there, it's dangerous to be on the hike within the Narrows because the river itself, its stage or its level can rise up over 20 feet in a matter of 15 minutes, and people can drown that way. The book's example of a flash flood is the flash flood in upstate New York and Vermont as a result of Tropical Storm Irene that struck them. They got like 20 inches of rain in like a 48-hour period. And so what happened there is they saw over 2,000 damaged road segments like you see here. Guys, imagine if I-4 was damaged like this. How long would it take them to repair that? Ridiculous. Okay, so here, these are 300 damaged bridges, over 800 damaged homes. And here's some data from a local river. The local river has a height, normally a river stage, about 4 feet. During the flood stage, it rose to about almost 17 or 18 feet. So that's pretty high. That definitely flash flooded a lot of areas and caused a lot of damage. Ice jam floods, this occurs in areas where you have rivers that flow kind of northward towards the pole or southward towards the pole, so depending on the hemisphere. But the book's example is in northern Russia. Now I know not many of us live in northern Russia. So what happens is when you have rivers that flow northward in the northern hemisphere that go like towards the really cold areas like the Arctic, okay, the the mouths of the rivers are in a colder climate, so they might be dammed because of ice. But if you go to the headlands of the river, which are further south and warmer, that could build up a lot of kind of water pressure, and then those ice dams may break as temperature rises and can flood an entire area. So that's a common problem in Siberia. I thought you guys should know. Then there's dam failure floods. The most notable one in Florida was, I think it was in the 20s, when Lake Okeechobee overflowed and flooded South Florida after a hurricane that passed through, dumped a lot of rain. But dams are designed to contain large volumes of water, and they can fail. You know, if there's an extreme event, lots of rain from a hurricane, or it's damaged for whatever reason, when a dam fail can release a lot of water and cause a flash flood. Oh, here are those north flowing rivers in Russia. So these areas here are warmer, right? So, and then the headwaters that are higher elevation, so all this water is flowing northward into a much colder region over here. So these areas might be, like there might be ice here that dams up the river. And so these areas here might not receive a lot of river water because there's an ice jam here. But then as more and more warmer water comes in here, melts that ice dam and then floods the river valley in this region. So people over there have to deal with that problem. Okay, so floods, they occur or reoccur on certain time frames or intervals. And an estimate on how often a flood of a given size, so because there can be floods of varying sizes, there can be really large floods with a lot of volumes of water or smaller ones. We refer to them as events that occur over a certain period of time. So a 25-year event would be a much smaller, but 4 times more likely to occur than a 100-year flood. So what a 100-year flood is, every 100 years, this flood will happen. Odds are a flood of this size will happen once. A 25-year event is a flood of this size would occur on average every 25 years. But it doesn't, you could have 2 25-year flood events back to back. It's just a matter of risk and probability. Okay, so what a 100-year flood means essentially is that there's a 1% probability in any given year for a flood of that size to occur. Okay, but in order to get a good estimate, you have to have years of data, and that can be adjusted. And the problem is that like once you have 20 to 30 years of collected stream gauge data to give you accurate predictions of how often these types of floods occur, it doesn't take into account global warming and the changes in climate and water movement in the atmosphere and big storm events. So what we may calculate as a 100-year flood may actually happen more often, or the probability might be higher because of climate change. So how do we control these flood measures? Well, we build artificial levees. All right, so some mounds are built on riverbanks to increase the capacity of the channel. So we build up on the riverbanks so that if the stage of the river ever rises, it won't overtop the banks. Those are artificial levees instead of the natural ones. And then there's channelization. This is kind of when you go into a river and you make it deeper and narrower, so that kind of forces the water to go out to the base level quicker. We do that a lot in Florida. We call them canals. And we often channelize them, or we have to kind of dig through them every so often so that we can make sure that any runoff water leaves the area without flooding. So it makes the water flow more efficient. Okay, so it accelerates erosion. Here's an example of another devastating flood. This is Bird's Point, New Madrid floodway that they saw a devastating flood here. And other flood control measures, flood control dams. In Florida, our canals will have these kind of smaller flood control dams so certain areas of our canals can hold water, or certain reservoirs. In fact, we have a flood control dam as part of the south side of Lake Okeechobee, and so that's built to store water in the lake, and so that we can control and manage the use of the water on our landscape in Florida. In other places, maybe this is used to generate electricity, okay, but it's also used to manage the water use in certain areas. And that is particularly true out west because they have less water to deal with than we do here in Florida. But the best approach with rivers and floodplains is the non-structural approach. So we can, what we should do is basically limit development within floodplains or areas that are risk to flooding, because just let nature take its course and build up those areas with sediment and make those riverbanks higher through the natural levees.